In this short presentation, I will examine select option prices using Black-Scholes model and Merton model. There are 5 parts. First, a call option. A call option gives buyer the right, but not the obligation, to buy shares of the underlying stock at a specified price and time. Because it's a right, the payoff at expiration is non-negative. The Black-Scholes model assumes the stock price follows a log normal stochastic process. Using risk-neutral valuation, we can obtain an explicit formula for the pricing. In this formula, the volatility parameter is unknown, so we first estimate it from the historical data. Here is the historical volatility of Tesla stock using rolling windows. Volatility is clearly not constant, as is assumed in the Black-Scholes. It oscillates over time, typically between 0.4 and 0.8, with occasional spikes. To test the model, we examine the payout of call options under delta hedging. Delta hedging offsets the risk from changes in a spot price. As the spot price moves, both the option price and the delta changes. This requires frequent rebalancing. This figure shows the dynamic delta hedging for at-money options. The green curve is the discounted payoff without any hedging. The blue curve is the payoff with hedging, and the brown curve is the Black-Scholes pricing using historical volatility. We can see that this hedging significantly reduces the extreme outcome and closely track the Black-Scholes price. The same pattern holds for the out-of-money options and for the in-the-money options. We omitted the unhedged payoff since it's the same as the previous case. On a fixed day and expiration, option exists across many strike prices. Market price deviate from the Black-Scholes for any fixed volatility. Since the price is monotone in volatility, we can obtain the implied volatility from the equation. Here is the implied volatility for options with 2 months maturity. We observe the volatility smile. The implied volatility increases away from the spot price. Therefore, using historical volatility tends to underprice some options. This scatter plot compares historical and implied volatility. The implied volatility is often higher and with some clustering near the spot price. This clustering corresponds to the strikes near the spot price. In particular, for at-money options, the implied volatility closely matches the historical volatility. Black-Scholes assumes continuous paths. In reality, stocks exhibit jumps, for example, around the earnings. The Merton jump model incorporates this feature. We will first calibrate the Merton model using the market data. Then we will do the dynamic delta hedging using the Merton model. As you can see, this Syrian curve is the price given by Merton model. We need more adjustment, maybe refinement for the parameters. But what's important is that the delta hedging, despite the differences in pricing across the models, the hedging outcome are quite similar. So this suggests a degree of model independence in delta hedging. There are several extensions. The Hedging model, which treats the volatility as the stochastic process, and market observations often indicate heavy tails, which motivate the use of more general distributions. and machine learning, which can estimate the volatility surfaces with greater flexibility. We can also study the American options, which allow early exercises, and multi-asset hedging for illiquid markets. These are the directions for future work.